In this video, we are going to address solving right triangles. So these triangles have to specifically have a right angle, be a right triangle. I'll remind you of a couple of things real quick off the start. Most of what we're going to use deals with SOHCAHTOA. So that was addressed in a previous video, but make sure that you understand what SOHCAHTOA means, because that's how we're going to have to determine which trig function we're going to use to solve for what we don't know. When you are solving a right triangle, you need to find all three angles and all three side lengths. That is what solving a triangle means. Find all 6 of those things, 3 angles and 3 side lengths. You have to be given a certain amount of that information to start, otherwise we're not going to be able to find the rest. So in this triangle, the other thing I want to address before I start solving for things is this is a triangle that I would call ABC, where it's the angle A, the angle B, and the angle C. Notice how those angles are uppercase. And then we are going to call the side lengths across from those angles lowercase that same letter. So angle A we've got is 30 degrees, and side length A is the side length across from angle A. So it might help to, in one location, write out all of those things. So we've got angle A, angle B, and angle C. And then we also have side length A, side length B, and side length C. What we are given is that angle A is 30 degrees. We also know that angle C is 90 because that is our right angle. And then we have side length C, because that is across from the right angle, we know that that is 12. So in terms of our SOHCAHTOA relationships, we know that that the side length C is our hypotenuse, because that is what is across from the right angle. Okay, so to solve this right triangle, we've got to find the other 3 things that we don't know. Angle B, that part should be easy. To find angle B, we know that all 3 angles of a triangle have to add to 180. So if we just do 180 minus 90 minus 30, that will give us the angle B, which would be 60 degrees. So I know that angle B is 60 degrees. Side length A and side length B. It doesn't really matter which one you start with. What I do know, since I know that I've got angle B as 60, I can set up a SOHCAHTOA relationship using either one of my acute angles. I like to use the one that was given, but it's totally up to you. So I'm going to reference everything from this 30 degree angle. And so let's say I wanted to solve for side length A. Side length A is opposite that 30 degree angle. So I know I'm going to be using opposite, and I'm given the hypotenuse, so I'm going to use sine. So we are going to say that the sine of that angle, which is 30 degrees, is going to equal the opposite side length, which is A, divided by the hypotenuse, which is 12. So to solve for A, I would just simply multiply by 12. Do not multiply 30 by 12. We are multiplying the sine of 30 by 12. If this is a unit circle angle, we could get exact answers. If it's not, we just have to use the calculator. So you should know through our study of the unit circle that the sine of 30 degrees is simply 1/2, which means I'm going to have 12 times a half here, which is going to give me 6. So that is going to be the length of side length A. I will show you in Desmos how we could get that as well. The first thing I want to do if I'm using a graphing calculator is make sure I'm in the correct mode. And since we were referencing our angle in terms of degrees, I want to make sure I'm in degree mode on my calculator. So I'm going to click that wrench, I'm going to click degrees, and I'm going to type in 12 times the sine of 30. It's understanding that 30 means 30 degrees, not 30 radians, and so we get an answer of 6. Okay. Now, once we really get started in finding a lot of these things, you're going to have a lot of options for what you can do to find like the last side length. One option would be I could set up another SOHCAHTOA relationship, and I could really use any of these relationships because I have a lot of information now and I'm just looking for this last side length. I could do the exact same setup but use cosine because it would be the adjacent side instead of the opposite side. And so I could say like the cosine of 30 degrees equals b divided by 12, in which case I would just get 12 times the cosine of 30 degrees. That's one option. One option that a lot of people are going to take is if it's a right triangle, we like to use the Pythagorean theorem, and you can do that. If you wanted to solve for side length b, you have side length a, you have the hypotenuse, which is 12. So I could also just say that 6 squared plus b squared is equal to 12 squared, and I could solve it that way. It's totally up to you what you want to do at that point in time. So if we did this, we would get that b squared equals 12 squared is 144, and I would subtract the 6 squared over, which means I'm going to subtract 36. So I would get that b squared is equal to 108, and then I would just need to take the square root of that, which would give me, I could use my calculator for that. The square root of 108 is about 10.4, and so I will just say that side length b is 10.4. Again, if you really understand your trig ratios, I actually think that it's easier to simply just switch the sign out for cosine and go that route to find b. But you do always, once you have two of your side lengths dealing with a right triangle, you do always have the option of the Pythagorean theorem. Okay, so that's the idea of solving a right triangle. If you are asked to solve an entire triangle, that means you need to list all three angles and all three side lengths. Below, I'm going to go through some word problems where we are just looking at applications of right triangle trig, which means we're not going to be asked to solve the entire triangle, but we are going to use SOHCAHTOA, we're going to use Pythagorean theorem to solve for specific aspects. So number one, a giant redwood tree casts a shadow that is 532 feet long. Find the height of the tree if the angle of elevation of the sun is 25.7 degrees. So I've got a tree. Its shadow is 532 feet long. So the shadows are on the ground. I often get students that put shadows as the hypotenuse. That would be incorrect because shadows are on the ground. They do not have any kind of height to them. Find the height of the tree if the angle of elevation of the sun. So angle of elevation means from the horizontal looking up. So I got to go across the top of this tree, and the sun would be up here because that is what is creating that shadow. But I want to find the height of this tree. And so I've got this right triangle now where I know that this angle of elevation is 25.7 degrees. I want to find the height of the tree, so I'm going to call that x. And what I want to think about is what trig function would I use given the information that I have. So from this acute angle, I have the adjacent side, and I'm looking for the opposite side. I don't have anything at all about the hypotenuse. So if I'm trying to use a trig ratio that relates the adjacent side and the opposite side, that means I want to use tangent because that's opposite over adjacent. So I'm going to say that the tangent of 25.7 degrees, clearly not a unit circle angle, so I'm going to have to use my calculator here, is equal to the opposite side over the adjacent side. And I would simply multiply by 532. And x is going to be 532 times the tangent of 25.7. And I already know that my calculator is in degree mode, so we're good. So we get about 256 feet. So I will say that x is equal to 256 feet, and I know it's feet because the shadow was also given in feet. That is the height of our tree. Next one. From a point on the ground 500 feet from the base of a building, an observer finds that the angle of elevation to the top of the building is 24 degrees, and that the angle of elevation to the top of a flagpole atop the building is 27 degrees. Find the height of the building and the length of the flagpole. So we've got a building, and in that building we also have a flag on top. We have 500 feet from the base of that building. We've got someone down here that's looking up at the top of the building, and the angle to the top of the building is 24 degrees. I'm going to start with just that. The first thing I want to do is find the height of the building, so I can basically do the exact same thing we just did for the tree. To find the height of that building, I'm just going to call that height x. I've got a right triangle, and again I'm going to use tangent because I'm looking for opposite the 24-degree angle, and I have adjacent. So I will start with the tangent of 24 degrees is equal to opposite over adjacent. I'm going to multiply by 500, and 500 times the tangent of 24 degrees is 222.6. So the height of the building is 222.6 feet. Additionally, we're given this information that the angle to the top of the flagpole from the ground, this angle right here, is 27 degrees. Okay, that's from the horizontal all the way up to the top of the flagpole. If I want to find the length of that flagpole, I have to make sure I'm using a right triangle. So what I have to actually do is talk about this height, which would be from the horizontal, which is from the ground, all the way up to the top of the flagpole. I'm going to call that y, because I've already used x. But I can't simply just like look at this distance between the flagpole and the building, because if I did that from this 27 degrees, I'm not dealing with a right triangle there. In order to make this whole thing a right triangle, I have to go horizontal all the way up. And so if I do that, basically it's going to be the same calculation that I just had, but we're going to use 27. So the tangent of 27 degrees is equal to y over 500. Again, multiply by 500. So I'm going to get that y is equal to 500 times the tangent of 27. So I'm just going to change this angle from 24 to 27. That's going to give me 254.8. 254.8. Now that is not the height of the flagpole. Okay, that's the height of the building plus the flagpole. So if I want the height of the flagpole, I just need to take this 254.8, and I need to subtract the height of the building, which we already found to be 222.6, and that's going to give me 32.2 feet as the height of the flagpole. Okay, last one. A 40-foot ladder leans against a building. If the base of the ladder is 6 feet from the base of the building, what is the angle formed by the ladder and the building? So this one's going to be a little bit different because I'm being asked to find an angle and not a side length. So I've got a building. I know that I have a 40-foot ladder that's leaning against this. So I'll even make it look like a ladder this time. That's 40 feet. If the base of the ladder is 6 feet from the base of the building, so I know that this distance right here is 6 feet. What is the angle formed by the ladder and the building? Well, you need to be very clear on which angle it is that you're trying to solve for, and be sure about that. Because what we have is, we have the ground in the building, that's a 90-degree angle. We also have like the angle formed by the ladder and the ground, which would be this one down here. But we're being asked to find the angle formed by the ladder and the building, which means we're being asked to find this angle up here. And anytime that our angle is the unknown, I'm going to use theta to represent that unknown. Instead of using x, I'm going to use theta. That tells me that what I'm trying to find is an angle. What trig function are we going to use? We need to start there. So what I have in dealing with this angle is I'm given the opposite side, and I'm also given the hypotenuse. The hypotenuse of this triangle is 40 feet. That is the length of the ladder. So if we are dealing with opposite and hypotenuse, we're going to use sine. So what I would have is that the sine of the angle, which I don't know, is equal to the opposite side length divided by the hypotenuse, so 6 over 40. And if I want to then solve for the angle, the way that I undo the trig function, whatever that trig function happens to be, is I have to use inverse trig, which looks like this. It's almost like a -1 exponent. The inverse sine, so that's like a -1. The inverse sine of the ratio 6/40. Okay, so inverse sine of 6/40. Now, be very careful about what mode you're in, because when we do inverse trig, which we're going to find down here and go to functions, and we've got them all right here, inverse trig functions. So I'm going to do inverse sine. This is going to tell me an angle. If I'm in degree mode, this is going to tell me the angle in degrees. If I am in radian mode, it's going to tell me the angle in radians. Now notice how all of these answers changed when I switched from radians to degrees, vice versa. So I want to make sure, you could give me either, but I think what makes sense for most of us when we're talking about angles is to use degrees. And if I'm in degree mode, this tells me that the inverse sine of 6/40 is 8.6 degrees. So that tells me that our angle is 8.6 degrees. And you want to make sure that the answer you give me makes sense. So this is a 40-foot long ladder and it's only 6 feet away from the base of the building. It would make sense that this would be a pretty small angle. This angle down here should be much larger, right? And again, that should make sense. So if you got something like 80 degrees up here, that doesn't make sense. Okay, that would mean that your ladder would basically be almost on the ground at that point in time. So make sure that your answer makes sense, but anytime you are solving for an angle, make sure that you use inverse trig to find that.